Hello, everyone. Good afternoon. Hope you're doing well. Nice little discussion on the chat. Thank you for that. Um, okay, we are a day away from the exam. So the first exam is tomorrow. Don't forget that. The exam opens at 11 a.m. It closes at midnight. Once you start, you have 70 minutes. It's all multiple choice. 30 some odd questions. Remember that you can use the one-page cheat sheet that you prepare ahead of time, piece of paper, pencil, calculator, and the periodic table and the table of contents that I sent you. Okay, and that's all you can use. You can't, if you use anything else, you're cheating. All right, please don't cheat. The exam is very similar in format. Those of you that had the class last semester, you know it's the same kind of deal. So there's no real big surprises. If you take the pretest, that's a good measure of what the exam will be kind of like. It won't be the same questions, obviously, but it'll give you a sense of what the exam will be like. Okay, I think it's 31 questions is what I have on there. Okay. All right, so today we're just going to finish up catalysis and do a quick little review for the exam. That's all we have. And then afterwards, I will stick around and answer any last minute questions or anything you would like to ask me. Okay. So, and I'll stick around as long as you need me and as long as there are questions. Are there any questions before we get started about anything? Okay, I don't see any questions. Very good. All right, so let's just finish up this last little topic of catalysis. It'll just take a couple minutes. There isn't really a lot here. So a catalyst is, the definition really has two parts. One is a substance that speeds up a chemical reaction without being consumed by it. So, you know, for example, one of the reactants, obviously, if you increase the amount of a reactant, that increases the rate of reaction too, especially for a first or second order reaction, right? But that's not a catalyst because a reactant is consumed by the reaction, all right? A catalyst is a substance that speeds up a chemical reaction without being consumed by it, okay? The way it does that is it provides an alternative mechanism or an alternative pathway with a lower activation energy. Okay, it provides an alternative mechanism with a lower activation energy. So for example, ozone, which is present in our stratosphere and acts as a shield for UV light, can decompose or break apart by reacting with an oxygen atom to form two oxygen molecules, all right? And that happens naturally in our upper atmosphere. And so ozone is naturally depleted, but naturally replenished as well. And there's sort of an equilibrium to that. But this process is very slow. A few years ago, there was problems with ozone being depleted more quickly because we were adding chlorine to the atmosphere through chlorofluorocarbons. And so chlorine, it turns out, was a catalyst for the depletion of ozone. So it provided this alternative mechanism. So this was a one-step mechanism, right? One-step reaction, but it was very slow, which means it had a very high activation energy, all right? With a catalyst, this chlorine would get up there and it would react with ozone, form O2 plus ClO. That was a fast step. And then the ClO would react with oxygen and form O2 plus Cl, right? And overall, then that adds up to this very same reaction, right? And the chlorine, notice, does not become consumed because it's consumed in this first step, but then produced in the second one, right? So that's a traditional definition of a catalyst, right? It's acting as a catalyst, provides an alternative mechanism that's much faster, right? If we look at the energy diagram for those two, so this is the uncatalyzed reaction right here. You see it has a very high activation barrier, The catalyzed reaction has 2 steps, right? But each step has a much lower activation barrier, right? So that happens much faster then as a result, okay? There are different types of catalysts. There are heterogeneous catalysts and, homogeneous catalysts and heterogeneous catalysts. A homogeneous catalyst is present in the same state or in the same phase as the reactants, right? So, for example, chlorine here, since it's in the gas phase along with the ozone, is an example of a homogeneous catalyst, right? It's present in the same state as the substances that it's being a catalyst for, all right? Heterogeneous catalysis involves a catalyst that's in a different state. So for example, you could have a reaction that happens in the gas state and a catalyst that's a solid, right? That would be an example of heterogeneous catalysis, okay? So for example, hydrocarbons like this often have these double bonds, and these double bonds can react with hydrogen to what's in a process called hydrogenation, where the hydrogen adds to this compound. And oftentimes these reactions can be sped up with a metal catalyst, all right? And again, this is an example of heterogeneous catalysis. You have a substance like ethene, it gets on the surface, it crawls around, you get hydrogen, it gets on the surface, the hydrogen bond breaks on the surface, it crawls around, they find each other, and then the product desorbs, all right? And this is just one way that catalysts can work. This is important, this kind of catalysis is important in your catalytic converter in your car. So your car has this thing called a catalytic converter that takes the exhaust, which has some nasty stuff in there like carbon monoxide, which is a poison. It has unburned hydrocarbons, which can result in the formation of ozone in the air. And ozone, although ozone in the upper atmosphere is a natural part of our atmosphere, ozone in the lower atmosphere is very reactive. And it's kind of the thing that makes your eyes kind of watery on a really smoggy day in LA, right? You may have experienced that. So that's what these partially burned hydrocarbons, that's what this represents. These compounds, if they get in the air, they'll actually promote the formation of that ozone. And then NO2, which is another very reactive gas. This is the gas that's responsible for the sort of brown colored air that you see sometimes on real smoggy days, right? And this catalytic converter basically works kind of like this. It has surfaces in it where these things absorb and they react. And instead of being these nasty things, it comes out as nitrogen gas, which is a normal part of our atmosphere, water, which is also normally in our atmosphere, and CO2, right? And of course, CO2 is a product of fossil fuel combustion. But we'd much rather have CO2 than CO, right? Because CO is actually much more poisonous than CO2. So these catalysts do important things. They speed up these reactions. Without this catalytic converter, those reactions essentially are so slow that they wouldn't happen, okay? By the way, this is one reason that we've seen huge decreases in pollutant levels in every major US city. So this is the change in pollutant levels in the United States over time. This is 1980 to 2013. Pollutants like NO2 have decreased by 60%. Ozone, again, lower level ozone, which is a pollutant, has decreased by minus 33%. And carbon monoxide has decreased from 84%. In 1980, all of these pollutants were much worse, right? So it's gotten a lot better because of catalytic converters. An enzyme is a biological catalyst. So one way our bodies can control reactions is by speeding them up. And this is done with enzymes. And enzymes are large, complicated protein molecules, and they can bind, they have a site on them called the active site that can bind the molecule that is going to be acted upon. That's often called the substrate. And it's kind of like, if you've taken biology, you might have seen this sort of lock and key kind of mechanism where the substrate fits perfectly into the enzyme. And then once it's bound there, it can react. That enzyme acts to lower the activation energy for the reaction, right? And you get a reaction, and then you get the products leaving, all right? Here's a real world example. When we eat sugar, it needs to be broken down into glucose and fructose. It does that. The bond that has to be broken is this one, okay? But this reaction has a high activation energy, and as a result, it's very, very slow. But we have an enzyme called sucrase, which binds the glucose. The sucrose like this. All right, and what it does is when it binds to the enzyme, it strains that bond, so it weakens it, right? And by weakening the bond, it lowers the activation energy. It makes the reaction much more rapid, right? And so it can bond on there, it weakens, and then it can desorb, and it turns into glucose and fructose. All right. So these kinds of reactions are present all over many of our metabolism systems, and virtually everything in biological systems is controlled by these enzymes. Okay. And when you take biology, you'll learn more about that. But that's really all there is to catalysis. Those are the things I wanted you to know. Do you have any questions?
Yeah, for the car example, did they change that on purpose to make it less pollutant, or was it just?
No, that was all these decreases are a result of the Clean Air Act and its amendments. And the Clean Air Act and its amendments basically required cars to have catalytic converters. So now if you own a car, you have to take it in for a smog check periodically, right? And they're just checking to see if your catalytic converter is working. And that has made a huge difference, right, in the pollutant levels. So that was on purpose, yeah. Taylor?
Can you go to the first, I think it was the first slide with the energies?
This one?
Yeah, that one. Do the two humps add up to the big hump, or is it just lower? Like, does it split it in half, basically?
Not necessarily, no. It could be anything, right? It could just be one hump that has a lower activation energy. This is just the case for this one, but it turns out it's easier to get over two small humps than it is to get over one big one, because thermal energy is enough to get you over these fairly quickly, but it's not enough to get you over this.
Okay, so it can really be any number of humps. It just makes it lower, basically.
Right.
That's all it does.
Right. In this case, I'm just showing you this is the actual mechanism, and this is essentially what it does. But it could be another one-step mechanism. It could be a 5-step mechanism. It just depends on the system.
Okay, it's more efficient. A good way to think of it.
The best way to think about it is it has a lower activation energy.
Oh,
which means it's faster.
Which makes it faster.
So remember, a catalyst only increases the rate of a reaction. A catalyst cannot make a reaction happen that wasn't going to happen anyway. Right?
Okay.
In other words, whether a reaction is going to happen depends sort of on the relative levels of these two things. And all the catalyst does is it lowers the transition state to make it happen faster. But if you have something here and then something up here, a catalyst can't help you.
Okay. It just helps with the speed of it.
With the rate, right? That's why I'm covering it here at the very end of the chapter on reaction rates.
Okay. All right. Thank you.
Yeah, no problem. Abe.
Yeah, I was wondering if you could go back to where you're talking about the heterogeneous catalyst. Yeah, right there.
Yeah, heterogeneous. The only difference between these two things there's two different types of catalysis. One in which the catalyst is in the same state as the reactants and products. So for example, if the reactants and products are a gas and the catalyst is also a gas, then that's homogeneous, right? It's all in the same state.
Okay.
In many cases, though, the catalyst is in a different state than the reactants and products. Like here, the reactants and products are gaseous, but the catalyst is solid.
Okay.
Does that make sense?
Got it.
Okay,
Mhm.
cool. Good. Ryland.
So we defined catalyst, but never really catalysis. Is that just sort of a reaction that includes a catalyst?
Yeah, correct.
Okay, cool.
Yeah. Okay. Any other last minute questions before we get on to our review? So the exam. You guys hear me okay? Okay, good. The exam is going to cover chapters 12, 14, and 15. So let's go through each one real quick. Chapter 12, remember that was the chapter on solids, liquids, and intermolecular forces. We learned about the different types of intermolecular forces, dispersion forces, dipole forces, hydrogen bonding ion dipole forces, right? So make sure you know what all of those are, of course, and how to predict whether a molecule will have those or not, right? And you can predict things like relative boiling points based on assessing what kind of intermolecular force is present in a particular molecule or compound, okay? We talked about some of the results of intermolecular forces like surface tension, viscosity, and capillary action. So make sure you know what those are, know how those vary with temperature, right? And know how those vary with the strength of intermolecular forces. We talked about vaporization and vapor pressure. So know what those processes, know what vaporization is, of course, know what vapor pressure is, know how vapor pressure depends on temperature, okay? We learned about fusion and sublimation. So know what those are. By the way, you should also know the energetics of these things, right? So for example, we know that vaporization is endothermic or exothermic. Is vaporization endothermic or exothermic?
Endothermic.
Endothermic, right? And fusion is melting, right? Fusion is melting. And then, so fusion is also endothermic. Same for sublimation. The reverse of all these processes then are all exothermic, right? So condensation is the reverse of vaporization. Freezing is the opposite of fusion. And deposition is the opposite of sublimation, all right? And then lastly, phase diagram. So know how to navigate your way around a phase diagram. In the book, at the end, you'll find these little chapter objectives that lay out a bunch of skills that I sort of expect you to know. And so those of you that took the class last semester, of course, have seen these before. These are the ones for chapter 12, right? So determine the intermolecular forces acting between molecules. The nice thing about this is it gives you some examples that you can look at, right? And some practice problems you can do to practice these skills, okay? Predict physical properties based on intermolecular forces, right? Be able to predict things like melting point, boiling point, especially relative to other compounds. Perform calculations using the heat of vaporization, right? Things like how much heat is required to vaporize 10 grams of water, right? Use the heat of vaporization to be able to calculate that. There's a section in the book on the Clausius-Clapeyron equation. We did not cover that in class, and that will not be on the exam, so you don't have to worry about that. Perform calculations using the heat of fusion. So that's very similar to this. This is vaporization. This is melting, right? So be able to do calculations like that. Calculate heats related to heating and cooling curves, right? So we talked about the heating curve for water, right? Where you increase the temperature and then you get to where it starts to, let's say, if you have ice, it starts to melt and the temperature stays constant for a while, right? Until all the ice melts. And then you can start to heat it again. So be familiar with that process. And then identify physical properties of a compound from its phase diagram. And by that, I mean, is it a solid, liquid, or a gas? And then be able to navigate in the phase diagram. And by that, I mean, what happens when the temperature changes or the pressure changes, okay? Chapter 14, concepts. So chapter 14 is the chapter on solutions, right? So we spent a lot of time on solutions. There's a lot of concentration units, right, for solutions. And that can be pretty confusing, right? So you want to make sure you spend some time learning about the different concentration units. Make sure you understand them all, right? Work problems where you have to convert between them, right? And so yeah. Okay, so anyway, know what a solution is. Know about solution and energetics of solution formation, right? Know about the solution equilibrium and the factors affecting solubility. So for example, what happens to the solubility of a gas as you increase the temperature, right? Or what happens to the solubility of a solid as you increase the temperature? Or what happens to the solubility of a gas as you increase the pressure? That's what I mean by factors affecting solubility, all right? And then all the units, right? Molarity, moles per liter, molality, molarity, moles per liter solution, right? There's some details in here that are very, very important that will bite you if you're not careful, right? Molality, moles solute per kilogram solvent only, not solution. Mole fraction, mole solute divided by total moles. Mole percent, which is just mole fraction times 100%. Percent by mass or volume, and that includes mass percent or parts per million or parts per billion, okay? So all those different units, make sure you know how to work with them. Then we talked about a bunch of colligative properties. So make sure you understand those. Vapor pressure lowering, freezing point depression, boiling point elevation, and osmosis and osmotic pressure, right? And then make sure you understand the effect of ionic solutions on all of these, right? When you have an ionic solution, you have to take into account the dissociation of the compound, right, to form more particles. So if you dissolve 1 mole of sodium chloride, you actually get 2 moles of particles in solution, right? And that means that it affects these properties, all right? Chapter 14, key skills. Be able to understand the solubility rule, like dissolves like, right? So be able to tell, for example, if you have a polar solute, that means that that will dissolve in a polar solvent, right? Non-polar solutes will tend to dissolve in non-polar solvents. Analyze energy transfer for the formation of a solution. What I mean by that is, remember we talked about these forces between solute-solute, solvent-solvent, and solute-solvent, right? So understand the nature of that and how entropy will drive the formation of a solution, even if all those forces are the same, right? Then evaluate the solubility of solids and gases with changing temperature and pressure. And by that, I mean the same thing that I was talking about here, the factors affecting solubility, right? And then, of course, all the concentration units, be able to do calculations with those. And then determine all those colligative properties for a non-electrolyte, a non-ionic solute, and then be able to determine colligative properties for an ionic solute, okay? So you got to take into account that ionic solute when you determining colligative properties of those kinds of solutes. Okay, a lot of equations in this chapter. These are all the equations that you'll need to know. Henry's law, which relates the solubility of a gas to the pressure of a gas, right? As the pressure increases, the solubility increases, and this gives you that relationship. And then all the definitions of all these different concentration units, right? Molarity, molality, percent by mass, parts per million, parts per billion, right? Parts by volume, which is the same as these, but it's volume instead of mass, all right? Mole fraction, moles of solute divided by total moles. Mole percent, just mole fraction times 100%. Then Raoult's law, right, tells you the vapor pressure of a solution compared to the vapor pressure of the pure solvent, right? And all it is the vapor pressure of the solution is the mole fraction of the solvent, right, times the vapor pressure of the pure solvent, right? So if the pure solvent has a vapor pressure of 100 torr and the solution is 90% solvent, then the pressure of the solution is 90 torr, right? So it makes sense. We are not going to worry about the vapor pressure of solution containing two volatile components, so you don't have to know that. Then we have freezing point depression and boiling point elevation and osmotic pressure. So all these colligative properties. The equations that you see here are for non-electrolyte solutes, right? If you have an electrolyte like sodium chloride, you have to add in the I, right? And the I can just go either right here in this equation, here in this equation, and here in this equation, right? So for example, what is I for, let's say, sodium chloride? I is equal to what?
2.
2, right? You just look at how many ions form, right? If you have magnesium nitrate, right? I is equal to
3.
3, right? And so on, okay? All right. Good, so that's chapter 14. Then we move on to chapter 15, which is the chapter on kinetics, right? So the first thing we covered there was the definition of reaction rates, all right? And you had some problems where you had to work with that. Make sure you understand those definitions and how to relate reaction rate to changes in concentration of either reactants or products, okay? Then we talked about how the reaction rates depend on concentration, right? And that's given to us by the rate law for that reaction. All right? 0 order, first order, and second order were the ones we covered. You could have some non-integral order reactions, but they're not as common. All right, integrated rate laws, concentration versus time, right? You start out with a certain concentration of a reactant. How much is left after 30 minutes, right? Then you got to use the integrated rate laws. The effect of temperature on reaction rate. In general, as you increase the temperature, reaction rates tend to go up, right? The dependence of that, if this is the rate law, right? The dependence is in K, right? K is temperature dependent. And remember, K is equal to A e to the minus EA over RT, right? And that's the temperature dependence. And then we manipulated that equation to get the straight line form of that equation called the Arrhenius equation, right? And you can use plots that use the Arrhenius equation to measure things like activation barriers, all right? Then we talked about reaction mechanisms. For a reaction mechanism to be valid, two things must be true. The mechanism must sum to the overall reaction, and the rate law, the experimentally observed rate law, must match that predicted by the reaction mechanism. Okay. Ryland, question?
Will we be expected to generate plots on the exam, or will we simply just have to
No.
interpret them?
No plot. No, you'll just have to interpret them. You will not be having, there's just not enough time to make a graph on the exam, and there's no way to do that. So yeah, on that, I might say something like a plot of the rate constant for a reaction as a function of 1 over T gives a slope of blah, blah, blah. What's the activation energy, right? That's the kind of question you can expect. And then lastly, catalysis, pretty much just what we talked about today. Okay, key skills: be able to express reaction rates in terms of changes in concentration of reactants or products. Be able to determine the rate constant and reaction order from the method of initial rates, right? So when you look at the rate of concentration, rate of a reaction for several different initial concentrations, right? Be able to get the rate law from that and the rate constant. Analyze graphical reaction data using the integrated rate law to determine the reaction order and rate constant. Again, you won't have to do this. You won't have to plot anything, but you should know those relationships and know what produces a straight line, for example, for the different orders of reaction. All right. Do half-life calculations. Perform rate calculations involving the Arrhenius equation. And again, you won't have to plot anything, but in this equation, there is that 2-point form, right? So if you know the rate constant at 2 different temperatures, you can use the 2-point form to get the activation energy. Or if you know the activation energy and the rate constant at 1 temperature, you can get the rate constant at some other temperature. All right, and I'll show you that equation in a minute. Determine whether a reaction mechanism is valid, right? 2 requirements, has to add up to the overall reaction, and it has to give the right rate law. And then lastly, the effects of a catalyst on rates of reaction. All right. All right, key equations and relationships. So for this one, this is the definition of rate, right? In terms of the changes in concentration of reactants and products. For a given reaction, right, there's only one rate defined this way, but there could be different rate of changes for reactants and products, right? Given by delta B, delta T, delta A, delta T, right? They're all related to the rate by this definition, okay? The rate law for a single reactant and for multiple reactants. And then you have all these integrated rate laws, okay? All these equations that I'm showing you, you have to memorize or write on your cheat sheet, right? Because you're going to have them all at your disposal, okay? The Arrhenius equation, here's the linear form. Oh, sorry, what is that? I was going to say about this. Yeah, this gives you the reaction order, the integrated rate laws, right? The units of K and the half-life expressions, right? Important to remember that the first order half-life is independent of initial concentration, unlike 0 and second order half-life, which depend on initial concentration. All right, the Arrhenius equation, the temperature dependence of reaction rates, right? The temperature dependence is in this rate constant, and the rate constant is equal to that, and you can manipulate that to get this equation. And notice this is in the form of a straight line. Y is equal to mx plus b, right? And here, y would be the log of k, x would be 1 over t, right? So if you plot the log of k versus 1 over t, you get a straight line. The slope of that line is going to be minus the activation barrier over r. And the intercept is going to be the natural log of a. A, of course, is the pre-exponential factor or the frequency factor. This is the 2-point form of that line, right? So if you have the rate constant at 2 different temperatures, you can solve for EA. Or if you have the activation barrier and the rate constant at 1 temperature, you can get the rate constant at another temperature. Okay. Then we have, in terms of mechanisms, you have the rate laws for the elementary steps. Okay. So make sure you know those so that you can use that information to predict if a mechanism is valid. You don't have to come up with a mechanism, okay? You'll be given a reaction, shown the mechanism, and you'll have to be able to determine whether or not it's valid or not, or predict the rate law that that mechanism results in. Okay. And that's all 3 chapters. It'll be on the exam. So we have a little bit of extra time, obviously. I'll see if there's any general questions. An example problem for reaction mechanisms. Let me see if I could find a good one here to do real quick. I think, oh, you know what? I did one. Let me pull this up. I had this. Here, we can do this one. So I'll start taking questions here, and I'll do a couple of questions, and then I will officially end the class. And then if there's more questions, obviously I'll just stay as long as people need. So don't feel like I'm not going to go anywhere until I answer all of your questions. Okay. So don't feel worried about that. So let's look at this. So this is a possible mechanism for this reaction. Okay. And this question asks to predict the rate law. Okay, predict the rate law. But let's do two things. Let's see what rate law this predicts. We'll do that. But let's also just see if this mechanism adds up to that overall reaction, right? So if I have this mechanism, NO plus Br2 in equilibrium with NO Br2, and this step is fast, okay? And then I have NO Br2 plus NO goes to 2NO Br, and this step is slow. So first of all, does it sum up to the overall equation? Well, let's see. Cancel that. That's an intermediate, right? An intermediate is formed in one step and consumed in another, right? And then if I add these two reactions together, I get 2NO plus Br2 goes to 2NO Br. So does it add up to the overall equation?
Yes.
Yeah.
Yes.
It does, right? So that means that it could be a valid mechanism if the rate law predicted by the mechanism is consistent with the experimentally observed rate law. Now, this problem is not giving us the experimentally observed rate law, so we don't know. It's just asking us to predict what rate law this mechanism would result in, right? And I'm going to put in some K's here, some rate constants. This is going to be K1, which is K for the forward reaction. And this is going to be K minus 1, which is the rate constant for the reverse reaction. And this is going to be K2, which is the rate constant for that one. Okay. So the first thing you do when you are writing, when you're trying to figure out the rate law predicted by a mechanism, is you look at the slow step, right? So the slow step is this one, and you see that it's this plus that. So if we go back to our elementary steps, it looks like this form, right? A plus B goes to products. So we know that for reactions like this, the rate is equal to KAB, right? If it's an elementary step. So the rate here predicted would be K2, right? Times NO Br2 times NO. You with me so far? All right, awesome. So now we want to know, okay, there's a problem because there is an intermediate here, right? Remember, this was an intermediate. So we got to figure out how to get rid of that intermediate. How do we express the concentration of the intermediate in terms of other things that aren't intermediates, right? So that's where we're going to go to this first step, and we see that it's an equilibrium step, right? And because this step is fast and this one's slow, that can reach equilibrium. And remember, when you reach equilibrium, what does that tell you? That tells you that the rate of the forward reaction is equal to the rate of the reverse reaction. That's what it means to be in equilibrium. Okay? So now we can say, oh, okay, well, we can write the rate for the forward reaction. The rate for the forward reaction is equal, if this is an elementary step, right, we can write is equal to K1 times the concentration of NO times the concentration of Br2. Right? That's the rate of the forward reaction. And then for the reverse reaction, if that's an elementary step, the rate for the reverse reaction is equal to K to the minus 1 times the concentration of NO(Br2). Right? And then if those are equal to one another, then we can write K1 NO(Br2) is equal to k to the minus 1 times NO BR2. All right, and then we can solve that for the concentration of NOBr2. Concentration of NOBr2 is going to be equal to K1 times the concentration of NO times the concentration of Br2 divided by the concentration of divided by K to the minus 1. You with me? All right, so then I can say, oh, all right, perfect. So now that I know that, I can take this, right? And I can substitute it back into the rate law that I had written that had an intermediate in it, because now I know the concentration of the intermediate in terms of the concentrations of the reactants, right? So what that gives me then is that the rate is equal to K2 times K1 times NO times Br2 divided by K to the minus 1. All of this is that, right? And then times, I'm running out of room here, but I'm going to squeeze it in, times the concentration of NO. All right, so I'll write that again. Rate is equal to K2, K1 over K to the minus 1. Now notice that this NO and NO, it's just NO squared, right? So I can write NO squared times Br2. So, and then this, of course, would just be one big K because it'd be 3 rate constants multiplied together, right? But this is the rate law predicted by the mechanism. All right, and so this question then, of course, the answer is C right here. Does that make sense?
I have a question for the rate reverse. Is that going to be the product from the fast reaction?
The rate reverse would be, imagine this reaction written backwards. What would be the rate law for that reaction? And it would be, since it's in that case, the kind of reaction is this one, right? A goes to products.
Okay.
Does that make sense?
Mhm.
I have a question.
Okay, I have let's see, I have a bunch of people with their hands raised, so I'm just going to go in order here. Alex.
So like say that for your forward reaction, like the equilibrium reaction, like say that NOBr2 was NOBr2 squared. So then would you like take the square root of both sides?
Yes, exactly right. Yep.
So, okay, so then it would become K1 times NO to the 1/2 power times Br2 to the 1/2.
Correct.
Okay.
Yep. Good. Sophia.
And you said we just leave the K's out, like one big K, right? Do they cancel each other
Yeah.
out?
They just become one big K. In this case, it's showing the individual, in this question, it was showing the individual Ks here because it was, I gave them to you up here. But if you were to measure the reaction kinetics for this, the experimentally observed rate law would just have one big K here. You wouldn't be able to distinguish between these other Ks. In other words, if this problem also told you that the experimentally observed rate law was rate is equal to K NO squared Br2, let's say the reaction also gave you this, and it was asking you if this mechanism was valid, right? Then you'd say, aha, requirement number 1 was met here, right? Requirement number 1 is that it adds to the overall rate law. Requirement number 2 was met because this mechanism predicts this rate law, which is identical to the experimentally observed rate law. Does that make sense?
Yes, it does.
Jane?
What do you do if you have more than 2 elementary steps, like 3? Like, how do you know which to substitute into?
So you always go to the slow step and start there. All right. If the slow step
Okay.
is the first one, then it's pretty easy, right? So we did an example where the slow step was the first one here. So if the first step is slow, then the rate of the rate law that's predicted by the mechanism is just the rate law for the slow step, right? So in this case, rate is equal to K1 NO2 squared, right? It's when the second step is slow that it gets a little more complicated and you have to do what we just did right here. Okay?
Okay.
Ryland.
Why is it that only the first step seems to have a backwards and forwards reaction?
Great question. So the only way that a particular step can reach equilibrium would be if it was a fast step before a slow step. So that's why you're going to see this, right? You won't have time to reach equilibrium. Let's say you have a slow step and then a fast step. The fast step may never reach equilibrium. That will not. The reason that this reaches equilibrium is because there's a bottleneck here, right? So this builds up enough to be able to go backwards as well, basically. So that's the reason.
Thank you.
Alex?
So if your predicted rate law for the chemical reaction, like like you determine that from like the experimental data, or it gives you it. But then if your slow step has any intermediate chemicals in it, then you have to write those chemicals in terms of stuff that's in the rate law.
Correct. Exactly right.
Okay.
Yep.
And then, so what, like, do you pull, like, does the rate law come from the chemical equation after you've canceled everything out on both sides?
No. The rate law for a chemical reaction can only be measured experimentally.
Okay.
And we learned how to do that, right? The method of initial rates is one way to do it. Or you can try the different plots, right, that we saw. You can try the different plots, right? And that'll tell you what the order of the reaction is, right? So you can either do the method of initial rates to get the rate law, or you can get the method of initial, the different plots. There's no other way really to get the rate law for, in other words, you can't just look at the balanced equation and write the rate law. In this case, they happen to coincide, but that's generally not the case. This has to be experimentally determined. You can go from a mechanism, though, to a rate law, right? If you know that you have an elementary step where the collision is between this and this, then you just go to this table and you can predict the rate law for that step. And then you can predict the rate law for the overall mechanism, right? Like we did here.
Mm-hmm. So basically, if your slow step has no intermediate chemicals in it, its rate law is just what it is, pretty much.
Exactly, like in this case.
Yeah.
In this case, right? The first step was a slow step. It's NO2 plus NO2. There we go. There's no intermediate. So that's it. That's the rate law predicted by this mechanism.
Okay, cool.
Yeah, very good. All right, any other general questions before I officially end class and then just take additional more particular questions, or any more general questions?
I had a question, but I guess it can wait until
Okay.
you end the class.
Okay, I think what I'll do is I'll go ahead and officially end the class here. So remember, tomorrow is the exam. If any issues come up for you, I will be monitoring my email, right? So send me an email and I'd be happy to help you. Otherwise, thanks everyone, and have a great afternoon, and good luck on the exam tomorrow. Remember, don't stay up all night studying. You want to have a clear mind. You want to be well rested, right? Because again, the exam is going to be time constrained. So you want to be able to think clearly and go through and answer all those questions. All right. Do your best. I'll be over here rooting for you. All right. It'd be great if everyone did really well. You have the ability. I've seen you do it before. So do it again. Okay. Thanks, everyone. Bye.